Hello and welcome again to my physics online video lecture series. Today's video we're going to be beginning the discussion of the polarization of electromagnetic waves. This discussion is meant to be at an introductory level. It can be followed by students in an algebra-based or calculus-based introductory course with maybe a little bit of work on their part. I am not going to make this extensive. However, I am going to make more than one video about this topic. Today's video, I want to talk predominantly about what it is that polarization is and how can we sort of like polarize light the simple way. There's several ways of polarizing light. I'm going to look at one method of it in today's video. So the other thing is that I should note before continuing is that in most introductory textbooks, this topic, if it's covered at all, is covered in the section on wave optics, but it's kind of hinted at also in the section of electromagnetic waves. And I'm basically putting it kind of in the electromagnetic waves section of my lectures. So if you're following in order, I kind of expect you to have gone through the lectures on electromagnetic waves before doing this particular lecture. There are some textbooks, the Knight, Jones, and Field College Physics textbook stands out in my mind. I think that's a very good textbook, by the way, but they do have kind of a strange ordering of their chapters compared to some others. They have wave optics and then geometric optics before going into electricity and magnetism. Most authors actually put these topics after electricity and magnetism. And I think that this particular topic, polarization of electromagnetic waves, makes the most sense to do after you've covered electromagnetism. So that's just a word about ordering. I've taught courses using both orderings before, for what it's worth. And actively am teaching courses using both orderings. It's kind of a, which do you prefer? I am not going to spend too much time on review. There is really one thing to recall, which is, what is an electromagnetic wave? And basically, an electromagnetic wave, you have a time-varying E field, a time-varying B field, and the two are sort of like generating each other and helping to propagate. So in some sense, there is an E wave, there is a B wave. Both of these things are in phase with each other. Meaning typically when you're at a local maximum for the electric field, you're also at a maximum for the magnetic field and vice versa. But they are in perpendicular directions to each other. So they have the same period, the same wavelength, peaks line up, troughs line up, but they are perpendicular to each other. And the other thing is there's a direction of propagation. So direction of propagation is given by the pointing vector. And that pointing vector, recall, is named after a person. So it's not spelled like to point with your finger, but after pointing. And that pointing vector involves taking the cross product of E and B. So if the pointing vector S is given by the cross product of E and B, we can write that S is perpendicular to E is perpendicular to B, and B is also perpendicular to S. So we can kind of like make a complete loop of all this. So what does that mean practically speaking? Well, if I use, let's say, red to represent my electric field, if my electric field happens to do this in space and time, like at a moment in space, so that my field direction is along, I guess you could call it the vertical axis of this page, then my magnetic field, which I'll do in blue, will happen to basically do one of these guys, so that the field is pointing into or out of the page at different locations. And I'm just kind of drawing some of the vectors, not all of them, just to give you a general sense. Then that means that my pointing vector will be along this direction that's perpendicular to both. And I've kind of drawn them a little bit askew. But essentially my pointing vector will either be to the left or to the right. And it's E cross B. So in this case, it's actually pointing to the right. So this is locally what my pointing vector S should be doing. I guess I could label these as E and as B. So B is in and out of the page, E is sort of vertically up and down, and S is left and right, and specifically in this case to the right. So what's polarization then? Well, polarization basically is in some sense just referring to this fact that we have a direction for the E field to be oriented and a direction for the B field to be oriented. Now there are different types of polarization. There's linear polarization, there's circular polarization, there's elliptical polarization, and there's unpolarized light. What we're mostly going to be focusing on in these lectures is unpolarized and linearly polarized. So when I say polarized light, I'm largely just referring to linear polarization. What do they mean? Well, polarization direction is the axis along which the E field is oriented for your observer. So let's say that I happen to be observing at this location right here. What would my polarization direction be? Well, it would be basically along this vertical axis that I've drawn here. Now, why do I have to give it a particular direction? Because for the picture that I've drawn, the polarization is, we'd call it like vertical, no matter where you put the observer. And that's an effect of this being linearly polarized light. Okay, the E field is always in the positive or negative Y direction, let's say. All right, so what about the circular and elliptical polarization? What do those mean? Well, basically, circular polarization means that the E and B field are rotating as the light propagates. And so you can place an observer at some given location, and depending upon what time you measure the field at, you might get a vertical, you might get a horizontal, or you might get somewhere between. So polarization could be, let's say, this way, it could be this way, or it could be somewhere in between. Elliptical polarization basically means the same thing in the sense that it's rotating, so sometimes vertical, sometimes horizontal, but as it rotates, the amplitude also changes. With circular polarization, the amplitude remains constant. Now again, I'm not really going to dwell on these ideas of circular and elliptical polarization. I'm simply going to focus more in these lectures on linear or unpolarized. Unpolarized essentially means you have an E field in all directions. And that may not make much sense at this juncture. It'll hopefully make more sense when I explain how to get to linearly polarized light. But essentially, you can polarize light using several methods. You can reflect it and use a Brewster angle. You can use a birefringent crystal to shift typically from one polarization direction to another, or from circular to linear, etc. And you can use like a polarizing filter, like a Polaroid. Now, by convention, we usually, when we're referencing polarizing filters, like polarizing glasses, etc., we usually represent them schematically by using a circle or square and then an arrow. And what the arrow represents is the direction in which the E field must be oriented to be transmitted by this polarizer if it is an ideal polarizer. So what does all that mean? Well, if I have light and the light is polarized in no particular direction, usually we represent that by drawing a pair of arrows that are crossed with each other like this, and now the light is moving in this direction. And then I happen to have a polarizer, and the polarizer is oriented like this. Then the light that passes through the polarizer will only have a vertical polarization direction, like so. Whoops. Arrow should maybe be more like this. Okay. So incident light maybe has some component that, if it's coming towards you, is wiggling like this for the E field, and some component that's wiggling like this for the E field as it comes towards you. And you interact with the polarizer, and one of these two wiggles goes away. So it's sort of like having something like this and something like this. It's hard to coordinate that with my hand. This is doing this, this is doing this. We have the polarizer, and now only this component makes it through. The rest has been absorbed. So how does that work? Well, basically this material, we'll just say, like, blow it up so that we can see the macroscopic view, consists of some long chain polycarbons like this, basically. And there can be little branches off of the chain like so, but predominantly the chain is oriented in one particular direction. And actually it's oriented in the opposite or perpendicular direction to what I've drawn here relative to the arrow. So if my arrow is pointing upward, then this chain will actually be oriented horizontally. So let me draw the arrow this way so that it's more consistent. Okay, and then I have, there's a whole bunch of them, and they're basically, they've been sort of like heated and then allowed to cool, and all of them basically are oriented in the same direction for this treating process. Now imagine that you have an electron that is free to move about on these particles. Okay. Imagine that you have an E field that is oriented vertically. In other words, the E field is oriented in the same direction as these long chains. Well, this particle largely can zip along the chain, has quite a bit of motion along this direction that it can undergo. And so when an E field is oriented that way and hits it, it zips along, basically accelerates and absorbs that field. In the other direction, the horizontal direction, it's not very free to move back and forth, so it absorbs very little field. The result of this is, because the electron is more or less free to move in this direction quite a bit, and we assume, that this continues and so on. Because it's free to move in this direction quite a bit, if I have a field that's oriented in that direction, that field is very likely going to interact with that electron and be absorbed. Basically, if you accelerate a particle, if you cause the charged particle to accelerate so that it speeds up, you generally absorb from the electromagnetic field. If you cause it to slow down, you generally emit into the field. Essentially, the particle speeds up, absorbs part of the field, and then slows down but emits in a random direction. So if, on the other hand, your field is oriented in the direction that's perpendicular to this, if you have a field that's this way, that particle is not very free to move in that direction, and so is not very likely to accelerate much. You can maybe get a little bit of acceleration, but it's brief. This basically means that you might absorb a little bit of the field that is oriented in this direction, but for the most part, you're not absorbing electromagnetic radiation in this direction. I should add, by the way, that these polarizing filters, you'd call them like transparent in the same sense that, say, a pair of sunglasses are transparent. You can look through them, you can see through them just fine. Light can go through them just fine as long as its polarization is in the direction that is sort of parallel to the polarizing direction of the device. The device itself then absorbs light from the other direction, and as a result, you end up with light that is predominantly polarized along only the direction that the polarizer is oriented in. Now, in a separate video, I'm going to discuss a principle called Malus law, which actually gives you sort of a how much light should be absorbed versus transmitted for these polarizers. It's beyond the scope of today's video. I'm just trying to explain kind of conceptually with pictures or qualitatively what's this process look like. Note, though, that you can have unpolarized light. Again, that means light that has polarization along both directions, generally equally along both directions. And when that enters into this polarizer, half the light basically goes away and is absorbed, and the other half is transmitted. The half that goes away is the half that has some sort of polarization in the direction that's perpendicular to your polarizer, and the part that goes through is parallel to the direction of your polarizer. And again, keep in mind that these represent E fields. The B field is, of course, perpendicular to this, and we're focused on E fields. So in some sense, the big vocabulary term is polarization direction. And this is the direction along which the E field specifically is, you could say, maybe oscillating for polarized light, or for a polarized EM wave. Remember that light is, or visible light is, a part of the electromagnetic spectrum. Okay. And the act of being polarized, so if the light is polarized, then it has a polarization there. And that polarization, again, the direction I've been using like vertical and horizontal, but it could be any direction. So if I'm looking down the pointing vector, such that the pointing vector is like this, S, then this right here would represent polarized electromagnetic radiation. This one right here, again, we're looking at the pointing vector straight on. This one right here is polarized. This one right here is not polarized, or at least has some superposition of polarizations. So if I have measurable E fields along all of these directions, this means that it's not polarized. If I'm measuring fields like this that are 180 degrees opposite each other, this counts as polarized. So this is my E field, this is my E field, this is my E field. And we have polarized, polarized, and this is not polarized. And that's all that I'm actually going to try to accomplish in today's video. Again, reminder, we're talking mostly about linear polarization, means we have only one direction in which the field is polarized. If I happen to be standing here detecting light, and at one moment all the light is oriented along this axis, and at some other moment it's all along this axis, and some other moment it's all along still another axis, but it's always along one axis at any given moment in time, that's still polarized. So this one right here, still polarized. This one, still polarized. If I have one where it's kind of a skewed direction, like this is polarized. Any of those count as polarized. It's only if I'm measuring, and I'm measuring multiple axes along which there are electric field, that it is non-polarized. Or put differently, if there's no axis along which the field falls to zero, then it's not polarized. I can, of course, measure polarization along any arbitrary axis for either of these, any of these three, and that's what the basis of Malus law actually is. So if I were to be measuring along, say, this axis right here, I would actually measure a polarization. It just would be different than if I measured directly along this axis. There is, however, an axis vertically where E is 0 when I measure it, and that makes this polarized. Okay, so that really is all for today's video. It's more qualitative than my normal. Don't worry, we'll get back to the sort of quantitative description of this in some future videos related to polarization. In the meantime, I hope that you've learned something from this video. As always, thanks for watching.